Today we will talk about the uncentrally principle. It is a difficult and interesting thing in chemistry. Then Nick will show you what it
has an
is.
equation, and that equation is delta x times mass times delta V is greater than or equal to Planck's constant over 4 times pi. Delta x represents the change in position, and delta V represents the change in velocity. And we can derive delta V and M into delta P. And what's important to notice about delta P is that, like V, they are both vectors, meaning they have direction with their value. Because if you remember with the laser experiment, we had, I don't remember, we can edit this, right?
Mm-hmm.
Yeah, okay. With the equation we just derived, we get delta x times delta P back is greater than or equal to h over 4 pi. Because these two values, when multiplied, have to be greater than the value of h over 4 pi, as the change in position of x decreases, the change in momentum has to increase. Because momentum is a vector value, as the change increases, we also get a change in direction. And the change in direction can explain the flattening of the laser in the laser experiment, because the change was on the x-axis. So there's that. I don't know. Did I miss anything?
Then I will make an experiment to show you how the magical and interesting this principle is.
Closer. You have it like right where the paper's flipped. So move your hands up, like up, up.
Up?
Yeah, there you go. You passed the light. There you go. Oh, you passed the light again. Go left. My left. You were right. Go right. Right there. More. 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 Closer. Bring your papers closer.
This is the equipment to show you how about the light spot to show the uncentrally principle.
The slit becomes narrower on the wall, so the spot gets narrow. At a certain point, the spot becomes wide, or you could say even horizontal. This happens because the photons of the light have become so limited at the slit that the laser passes through their horizontal momentum, and that momentum must become less defined to fit Heisenberg's uncertainty principle. By showing the laser experiment, we can get close to the position, but even then it becomes more difficult to determine the exact momentum, and vice versa. Therefore, there is a limit that is expressed by an equation.
This interesting principle must have a long history, start with the Heisenberg, and many famous scientists study with it.
Heisenberg was considered gifted by his teachers. He had a love for math and later studied at the University of Munich. In 2 years, he wrote 4 physics papers. After earning his doctorate in 1923, he studied with Max Born. After studying with Max Born, he studied with Niels Bohr in Copenhagen. In the early 1920s, physicists were having trouble with the current quantum theory. On small atoms, the theory was correct. However, on larger atoms, the theory ran into problems. Not to be outdone, Heisenberg joined in. He wanted something physical that could actually be seen, so he used the spectrum of light absorbed or emitted. He came up with a new formula of quantum mechanics that was matrix-based. No one wanted to accept matrix-based equations because they were hard to understand. Einstein also supported other ideas, so the matrix-based designs were not popular. Schrödinger, another scientist at the time, was testing his theory and found mathematically the Schrödinger wave equation and the matrix-based equations were similar mathematically. Many scientists preferred using the Schrödinger wave equation because it was in a format they understood. Schrödinger visited Heisenberg in Copenhagen, where they debated which was better. Other scientists combined the two and formed quantum mechanics. Quantum mechanics had faults in measuring position and momentum at the same time. Heisenberg said this was no fault of the experimenter, but it was a fault of quantum mechanics. He published a 14-page paper stating this, and this came to be known as the Heisenberg uncertainty principle.